Hi everyone, welcome to the lecture 2 on the theory of semigroups. So we have seen that the basic structures of semigroups can be developed from the theory of groupoid or the basic definition groupoid, and we have seen some examples of groupoids and semigroups. Now we are going to look at properties of some certain semigroups, or what are the properties that we can add to a basic semigroup. First, we will come up with the idea of commutativity. So commutativity. A semigroup S is said to be commutative if for any two numbers, okay, or any two elements of S, we must have xy equal to yx. This is the definition. So let us look at some examples. Some examples will definitely follow, like the previous examples we have already seen, like z plus, because addition is a commutative binary operation on z. Likewise, we can define multiplication. Okay, so this is a commutative semigroups. Now, what are the non-examples? One of the classic non-example is the collection of matrices under multiplication. For instance, I am taking 2 by 2 matrices over real numbers with multiplication, usual multiplication of matrices. It's not commutative. It's very clear that it is a semigroup, right? For instance, if you check with, we need only one counterexample in order to prove that it is not a commutative semigroup. We use this example. By simple check, you can see that is 2 1 0 0, and if you multiply the other way, you will get a different value, 1 1. That is it is not commutative. It's not commutative. So being given these examples, I'm just going to define what is a monoid. So we are going to define what is a monoid. Monoid. So monoids are actually semigroups. A semigroup S is said to be a monoid if there exists an element, say 1. This is a notation, right? Elements, say 1, such that for every S belongs to S, 1 times s equal to s times 1. Okay, so 1 times s means this is a map. If you multiply using the multiplication rule, the binary operation defined on the monoid, 1 times s equal to s times 1. So if there is such an element, we call this semigroup as a monoid. What are the quick examples? We can look at quick examples. Real number under addition is a monoid. How? What are the identity element? The identity is 0. If you add x plus 0, you will get x 0 plus x. So this is the identity element. So you note that the notation 1 here, what is 1? 0, right? It's like 1 equal to 0 sometimes. Yeah. I mean, what is mean by this? This is the identity element. Yes, here it is 0. So when you look at the multiplication also is a monoid, because the identity here is 1. If you multiply any number with 1, you will get the same one, including 0. Including 0, because if you multiply with 0, 0 times 1 equals 0, right? Any times 1, if you multiply with this, you will get the same number. Okay, you will get the same number. So that's an identity here. Okay, so also the non-commutative semigroup with the operation multiplication, usual multiplication in matrix, is a monoid. The identity element is the usual identity element in case of group of matrices. So what are the non-examples? Non-examples are collection of even integers 2z under multiplication, right? 2z under multiplication is a semigroup but not a monoid. Is not a monoid. But you have to note that, how do I say that it is not a monoid? In order to say it is not a monoid, you have to show that any element belongs to this semigroup cannot act as an identity element. For example, if I am arbitrarily, I'm just suppose in order to prove this argument, I'm assuming there is a identity. Suppose 2n belongs to 2z is identity element. Okay, this is for fixed n, because I'm arbitrarily, n is arbitrarily fixed. Why I'm telling arbitrarily fixed? Because I'm just telling any element here cannot be identity element. 2n, n is arbitrarily fixed. Now we look at what is the property of the identity element. If you multiply with any element, you will get back the same element. That means even if you multiply 2n with 2n, it will get 2n. This implies what? 4n square must be 2n. Being n is an integer, if n equal to 0, it's okay, right? But otherwise, if n equal to 0, what happens? The element 0 would be the identity element, but that is not true. N cannot be 0. If n is 0, if you multiply with all elements, you will get 0 only. You will not get back the same element, right? N times 0 is 0, not n. So 0 is not an option. So n not equal to 0, then we can cancel out this. Then what happens? You will get uh, 2n equal to 1, which implies n equal to half, right? But we have already assumed n is an integer, right? That is a contradiction. So n is an integer, that is a contradiction. So that means it cannot be a monoid. That means any element in any even integer cannot be an identity, cannot act as an identity in the semigroup 2z under multiplication. This group is very important. We will be this semigroup is important one. We will be using this in the coming sessions. So another property of this identity is whenever you are able to find an identity element in a semigroup, okay, then that identity will be unique, okay. So let us call that is a kind of result, right? So the result is simply S has at most one, I don't know this, at most one identity element. S has at most one identity element. That means the semigroup may not have an identity, but if it exists, then it will be the unique one. That is the idea. So suppose 1 and 1 dash be the identities of S. So in order to get a contradiction, I am using uh, an argument. Suppose you assume if there exists two elements, what is the problem then? Then definitely 1 dash equal to, what is the property of the identity? When you multiply it with any number, you will get the same number. So 1 dash can be 1 times 1 dash. It is because 1 is a identity. And also you know that 1 dash is an identity, so when you multiply with any number, you will get the same number. So you get 1 here. This is because 1 dash is a identity. That means what? 1 dash equal to 1, right? That's what we have proved. So 1 dash equal to 1 times 1 dash because 1 is an identity. 1 times 1 dash is equal to 1 because 1 dash is an identity. So in fact we have proved that the both are same, right? Yeah. So unlike in groups, there is a convenient idea in a semigroup that if there is no identity element in a semigroup, we can adjoin an identity. Okay, we can add an identity by defining some multiplication rules. So the next thing we are going to study, how can we adjoin identity element to a semigroup. So the next definition is going to be adjoining identity element to a semigroup. So we can write if a semigroup does not contain an int element, we can adjoin an identity element, say 1 to S by defining two conditions. Define two rules anyway. First one is for every S belongs to S, you multiply with this 1, you get back this. When you multiply with the left or right, you will get the same element. So this way I have defined the multiplication with every element with the newly adjoined 1. Now the problem is, what about if it multiplies with itself? Because because 1 is not belongs to S, right? So I have to define it separately. Simply define 1 times 1 is 1, right? So these are the two properties which defines a identity element, and we will denote this by S1. So S1 means S is a monoid, otherwise S union 1 in a descriptive way. So the main meaning is where S1 denotes a monoid, whether it is adjoined or it is naturally is there. Now the another definition is as zero element. What are zero elements? Okay, zero element. So we denote S has zero element if there is an element, say 0, such that for every S in S, 0 times S equal to 0 equal to S times 0. In the previous case, when you multiply with an identity element, you will get back the same element. In this case, when you multiply with a 0 element, you will always get 0 only. That's the idea, right? So it nullifies the effect of any element in the semigroup. So we can see example in Z having this multiplication is a semigroup with a 0 element. Zero element. In fact, it contains the identity also, right? So what about a non-example? Also, okay, again you can look at some more examples are coming. This is a semigroup with a 0 element. Okay. In fact, in 2Z we have found that it does not contain identity element. Now the another non-example it does not contain a zero element. That means when you do this, you will get the same thing, right? So let us consider Z under addition. What about this? Does it contain a zero element? So we assume, suppose it contains a zero element, right? Suppose there is a zero element. Then what happens for every natural number or every integer, right? N plus 0 equal to 0 or equal to 0 plus. But you already know that what is n plus. Okay, so this is idea, right? This 0 is not the natural 0 contained in Z. This is a 0 element. It can be anything. I'm not telling this is the 0 element, but this is our hypothesized 0 element, which is 0 bar. So this is the idea. Okay, but we know that n plus, these are the 0 element is also an integer. This means 0 bar minus 0, you will get the actual 0. That means n equal to 0 for every n, right? That's an absurd, right? If you take 7 is 0, 8 is 0. So that is a contradiction. That is, it does not contain, it contains no 0 element. Contains no 0 element. Okay. Now we are going to construct one important example, which is a semigroup without identity and 0 element. So a semigroup without, basically a finite semigroup without identity and without 0 element. Okay. So in order, we have to find a semigroup which does not contain identity element and does not contain a 0 element. So I'm just using in the previous example, as I have done already, I'm taking the set S equal to 0, 1. And I define a multiplication rule, define mu as follows. 0 times 0 is equal to 0. 1 times 1 equal to 1. 1 times 0 equal to 0. 0 times 1 equal to 1. Now, even if there is an identity and 0 element, it must be either 0 or 1. So first we will show there is no identity element. So in order to show there is no identity element, first I have to show 0 is not an identity. Okay. So 0 is not an identity. How? Because I have in the multiplication rule 1 times 0 is 0, right? It is not 1. If 0 is an identity element, what I have to get back? 1 times 0 must be 1, but in this case 1 times 0 is 0. So that is a contradiction. So 0 is not an identity element. And I have to say 1 is not an identity element. 1 is not an identity. Why? Because 0 times 1 equal to, in the definition, it is 1. If 1 is an identity element, what should I get back? I should get back 0. 0 times 1 should be 0. But that is not possible. That is not in the case. So 1 cannot be an identity element. That means this does not contain, the semigroup does not contain a identity element. Second thing is, there is no 0 element. So for that I have to show 0 is not a 0 element. Not a 0 element. How? If let us look at 0 times 1 is equal to 1. 0 times 1 is equal to 1. If 0 is a 0 element, 0 times 1 should be 0. Right? So that is not possible. Now 1 is not a 0 element. Because 1 times 0 in the definition is 0. If 1 is a 0 element, you should get back 1. Because when you multiply with the 0 element, you have to get 0 element. So if 1 were a 0 element, 1 times 0 must be 1, but here it is 0. So that is it is that is 0 and 1 are not identity and 0 elements. That is, in fact, this is this semigroup. The semigroup S mu is without identity element and 0 element. Okay, so there is one more thing you have to we have skipped in this proof, because I didn't prove this is an associativity. How do you prove the associativity? In order to prove associativity, I have to check all 8 pairs. Like, it's not pair, 8 triples. All this case you have to check associativity. I would give this as an exercise for you. You can check it. All this case, what you have to do? You have to check whether it is equal to or not. Check. In this case, it is always equal, because the same number. It will start from here. What is happens? Whether it is true or not. So you have to check all these things. If all these things are equal, then the associativity can be proved. So I have already proved in my notes, so you can check it. Okay, so this is an associative groupoid, that is, it's a semi-group without identity and 0 element. So by this I stop my lectures. In the next lecture we will study adjoining 0 element and the uniqueness of 0 element and some more advanced properties. Thank you.